This is a short and informal summary of the Emulate3D Tanks and Pipes catalogue, version 1. Before we look at some of the new features which this catalogue provides, let's remind ourselves on what Emulate3D can do. So the software allows you to build a digital twin of your facility. We have 3D graphics, a rigid body physics engine, a discrete event physics engine, a mechanism solver, and loads of tools and catalog items that allow you to build up a representation of your industrial equipment. There's a number of applications once you've got this digital twin built. The one we're going to focus on is controls testing. So we've got this nice model, and we might then connect it up to a PLC or a higher level controller or a load of PLCs, and we can trick our controller into thinking that it is running the real equipment, and we can validate its logic. And this can be for a really large system. This is a airport baggage handling system, so kilometers worth of conveyor and thousands of product. Or it could be a small system. We could be doing an emulation of a robot in a cell. We cater for a really wide range of industries, but the one thing in common is that we're dealing with discrete product. So as you see from all of these examples, we're dealing with solid parts that are being moved around, whether it's frozen goods, end-of-line packaging in this case, through to cans, through to boxes, through to tires, or cars for automotive, bags, this solid product. We traditionally have not dealt with process applications, so powders, bulk goods, fluids, gases, things like this. It's not to say that our customers can't represent these types of systems, because they can, because Emulate3D is a really flexible framework. We allow our users to write scripts to define their own custom behavior, and they can also connect up to external applications like MATLAB or ANSYS for really detailed physics simulations. Within Emulate3D, we are aiming to run our model of a large system at real time. So everything's running on your computer at the same speed as the clock on your wall. And this allows us to sync up with our PLC so that it has the correct behavior. Now, that kind of limits the level of detail that we can potentially put inside our model, because we need our computer to be able to crunch all those numbers fast enough that we stay synced with our controller. In some cases, though, we do need more physics detail. We can model this in, say, an abstract way, like using one of our black boxes, and an application for this might be something like filling and end-of-line packaging. Our filling machines will be dependent upon fluid being available to fill those cans, and we might not model that inside Emulate3D, but we need to get its effects, and we've got objects like black boxes which can produce the same resulting effects without having to do all those detailed physics calculations. We're seeing demand for higher fidelity modeling of these types of process applications. So rather than our users needing to go to MATLAB or ANSYS or write their own custom scripts, we've created our own catalog which allows you to represent tanks and pipes and fillers and mixing, pumps, valves, everything like this. This is a framework for streamlined fluid modeling, and it contains lots of catalog items that allow you to build up these types of systems inside Emulate3D. And we're aiming to get flow rates and behaviors which are accurate enough that we can trick our controller into thinking it's dealing with the real equipment and it's getting the right signals, so right times for fluid to be moved from one vessel to another. However, we want it to run fast enough that we can perform an emulation. So we talk about the complexity here. It's not our intention for Emulate3D to be the tool that you use to size your pumps or to work out the complex physics of your heating mixing processes. No. Instead, Emulate3D is just caring about the timings and the signals that are being sent by those sensors so that the controller thinks it's controlling the real equipment and then provides its own signals back, and we see how the physical responds and validate our controls. We obviously need some level of detail in order to get the right sort of flow rates. So within the catalog, we can define different fluids, and these fluids have their own density and viscosity properties. The fluids are tracked as they move around our system, and their volume is retained. We also track their composition as they mix together. They move around according to pressure, and pressure is applied by gravity and by pumps, and their flow rate is determined by the pipe's diameter that they're pushed through and the friction of the pipe. And we also have properties to give you global scaling and tuning as well. Our version 1 of the catalog is an approximation, and we provide those tuning parameters to allow users to get the accuracy they require. It's an approximation with controls testing being the aim and the application here. We don't model thermodynamics, we don't model chemistry, we don't model gases or powders. It is just fluids. So what would this look like? Here is an example where we're using catalog components, like we would with building anything inside Emulate3D. We are snapping together a tank with some pipes and connecting it up to a mixer, like so. And everything's parametric and snaps together nice and cleanly, meaning it's quite quick to create a layout. What we're interested in is how the fluid behaves here. So let's go and set up our system so it's got a valve between our mixing vessel and our tank, and a flow meter just to tell us what the flow rate is. We can then set up our tank so it has an initial fill when we start our simulation of water, which has its own liquid properties. And then we play the model, we see that the liquid flows up to the valve until we energize, open our valve, and then we see that just the force of gravity is moving our water here. And the flow rate decreases as the pressure in those two vessels equalizes until it drops to 0 and their heights are equal. So kind of what we would intuitively expect. And if we wanted to pump out the rest of that fluid, we would need to add in a pump to our system to apply additional pressure. So that's the basic ingredients. Let's see if we can build up a larger system and actually see how controls testing would work. Here we're going to mix together some syrups, some sweetness, some sugar, with water to create fruit drink. In this particular model, we are, in this particular model, we're using this matrix of mix-proof valves to give us many potential routes which fluid can flow through the system. And this is going to be controlled via our PLC. We can use our I/O browser to connect up to our PLC, and that PLC is doing what I did in that first video with opening and closing those valves, controlling it directly. We've also got plant PAX into the mix. This is the plant PAX representation, and we'll use this to start our process. So here we can go back and start creating orange juice, I think, or orange drink. Oh, blackcurrant. Here we'll start create some blackcurrant, and this is going to send a signal to our controller. Our controller will then run its logic for creating that batch of blackcurrant, and it's going to start pumps and open valves along the route as it understands it in order to start filling our mixing vessel. We'll need to wait a little while as this mixing vessel fills up, but we can instantly see if our controller is doing the right sort of thing, because if it wasn't set up correctly, then obviously we wouldn't be getting fluid into our mixer here. Now I said that we can define multiple types of liquid and also how they mix together. So what we've defined here is if we have a set ratio of syrup to water, then we create a different type of fluid. So as our process continues, you'll see that we start mixing in more. You see we're now bringing in sweetener into our mix, and the color is going to change, and we're tracking the composition of those liquids for debugging purposes of our code. And once we reach a desired ratio, especially when pumping some water, we will see that the liquid changes into a finished product. So for basic controls testing, we can first of all see if our system behaves as we anticipate. This is a validation that we've written our cycles correctly. And this will obviously include things like clean in place as well, so producing a longer cycle. What's interesting is this additional testing that's possible, these fault conditions that we can conveniently introduce inside Emulate3D. So inside this system, we could introduce a fault like, for example, one of our valves stalling. And if we do so, we can manually click on a valve inside our model, set on its property to make sure it stalls, and then see how our system responds, see how our controller responds to its given feedback, and does it provide the right reports on the HMIs, does it behave correctly? So if I skip ahead slightly on this video, you'll see that we can do exactly this. We can introduce a stall or a slow into our system. So here we've got some fault simulation properties. And we can go and introduce a stall to our system. We'll see, have we correctly accounted for that potential condition inside our controls code. So Emulate3D provides a test bed for our logic for these types of tanks and pipes applications. Let's look at another example. Here we are bringing in a few additional elements as well, so we might be mixing in some more liquids or even powders, and we might get delivery schedules of our product coming in. So this is bringing in our process to a slightly larger system. In this case, this is a liquid soap facility. So here we are pre-mixing some of our liquids, and then we're passing them into a main mix, and they'll continue on. So quite a wide variety of different systems which we can represent using this catalog. So one of the strengths of Emulate3D is how it already handles discrete applications. So that interface between our tanks and our pipes and the discrete world is going to be very important. And we provide a range of parametric filling components which you can use to model everything. So that CAN line we looked at as an early video in this presentation, we could have the mixing and all of the process being modeled and tested simultaneously with all of the end-of-line packaging. All of these components are parametric, which allows you to really quickly create the right representation of your system. And like how we do with other things inside Emulate3D, we also have the ability to mark up your own CAD to get the exact visual representation of your filling process. So this is a brief overview of our tanks and pipes functionality. I hope you find it useful. Please reach out with any further questions.